Yeah, good morning. Thank you for having me. Yeah, so there's been some discussion in the last days on various initial data solvers. And as I know Joshua mentioned in his talk on Tuesday, there's kind of a lack of publicly available codes. And so today I'm presenting our new public code that focuses on the generation of initial data for spinning compact object binaries. So I'm Sam Tootle, and this was done in collaboration with my colleague Jens Papenfort. And the link to our paper and our code is also here. Okay, my screen stopped. Presentation. Yeah, everything is freezing. Okay. For some reason, I won't switch back. So, there we go.
You want to try?
Yeah, here we no, it's good. Yep. So, yeah, yeah. So the motivations from our group was we focus a lot on merger dynamics, but obviously other people in the community might also be more interested in accurate waveform modeling on the in spiral. And so from the dynamics standpoint, we had a lot of interest in especially extreme configurations of binary neutron stars, as well as black hole neutron star binaries. For our analytical implementation, I know Heavy discussed the CTS formulation. We implement the extended conformal thin sandwich formulation, with the extended being the addition of this constraint equation on the laps. All determined under braces are obviously when you have some source, so a neutron star in our case. However, when we're just solving in case of vacuum, these are obviously neglected. One thing, and this is the reduced system of equations when assuming a flat background metric that's constant. In our case, the flat background metric is just the Minkowski metric in Cartesian coordinates, and we use the maximal slicing assumption. However, when we do solve with sources, so neutron stars, the system of equations we actually solve has this inclusion of a p over rho. So analytically, you look at this and you think this is kind of dumb because nothing's changed. But that's the point of it. The reason we do this is that spectrally, this is a much more well-behaved system of equations, and it removes the explicit dependence on rho, so our number density, which is spectrally misbehaves and results in a lot of Gibbs phenomena on the boundary, which I think was discussed a lot in Josh's talk on Tuesday. So this is just a clarifying remark on something that we do slightly different. And this also helps us reduce the need to do filtering of high order terms. And so you get a very consistent solution without having to do hand tuning or hand filtering of the matter terms. So our numerical implementation, FUKA, is based on the Cadet spectral solver. It's a fairly recent solver in the last 10 years or so. It provides a layer of abstraction so that equations can be entered in a LaTeX-like syntax. So it's very nice because you can actually see your system of equations in front of you and have an idea of how things are working together. Additionally, you can add new operators to the system. And this is essentially how we implement handling of the equation of state, for instance, as a module on the side that handles the equation of state in the background, and then is just called when needed by the solver. Initial data involving black holes are constructed using the excision conditions, such as those developed by Cook and Pfeiffer, with the initial assumption of quasi-equilibrium. So the Komar mass and the ADM mass are assumed to be equal. And in the case of initial data involving neutron stars, we can do piecewise polytropes or tabulated equations of state. On the tabulated side, we currently use the Lorraine format for equations of state just because it's very common, readily available, and we had plenty of them sitting around. This could be adapted to others if it was really necessary, but that's the way that it's set up right now. This figure at the bottom is just an example of the domain decomposition as done in Cadeth for, in this case, this is an asymmetric binary black hole system. Cadeth uses a bispherical decomposition in order to have a continuous coordinate system throughout the numerical domains. For those interested, I encourage you to read his Philippe's paper on the details of this. But the idea is that you get these spherical surfaces around your objects. That gives you nice resolution and allows the solution to be adapted. So in the case of neutron stars, we actually have adapted domains that can ensure that even in the high spinning, in those cases, the domain conforms to the geometry of the matter distribution. And then you have these bispherical domains on the exterior, which give you a smooth mapping between these two spheres. And then you have a compactified domain, which has a coordinate that goes as 1/r. So you're actually evaluating your integrals, so like the MADM or your ADM mass and your Komar mass at an actual, as close to an infinity as you can, right? We're not doing some arbitrary distance of like 10 to the 9th or something. Since the coordinates go as 1/r, we can actually say this is numerically infinite. So from the capabilities, so what's actually included? So FUKA is a collection of solvers. We have isolated black holes and neutron stars where you can do different spins and masses, and everything is fixed based on the mass and the spin. We don't do fixing of the central enthalpy or something like that, which for us makes the solvers much more intuitive to use. We do have binary black holes, neutron stars, and mixed binaries, with the limitation that the spins have to be aligned or anti-aligned with the orbital axis. This is a restriction on the spectral solver because there's a strict z-axis symmetry currently, and there's no near-term project to change that. There are some other possibilities, but that's for future work. This doesn't include the ability to do eccentricity reduction in a very intuitive manner, and we also ensure that the ADM linear momentums are minimized, so there's no drifts in your initial data after they've been imported into your evolution scheme. We tried to provide an extensible framework to continue the development. The idea behind this is that we tried to minimize the layers of abstraction in order to generate initial data, so that you can, for the interested users, whether you want to move on to scalar fields or something else, you don't have to sift through a lot of codes to try to, or a lot of separate codes to try to understand what we're doing. Everything's laid out in a fairly methodical fashion, and yeah, it's I think it makes it very easy to do future work with the codes that we've released. There's a version 2 that would be coming out that will make things a bit more automated, but with automation comes abstraction, and then you reduce your extensibility. Finally, this cross mark on the export interfaces is really with regards to we need more feedback from the community as far as how well these actually work. For the Einstein toolkit, it works very well, and yeah, it makes it very easy because we have the interface built into the library. You really don't need much code on the Thorn side in order to import the initial data. So in discussing kind of the results of our code, the things that we want to consider are error sources. So on the right is a convergence plot. I know Halvi and Josh both touched on error with regards to initial data and resolution of your evolution. So we have this idea that your total error is a function of how not constraint satisfying your initial data is, as well as the errors introduced by your evolution scheme, as well as the finite resolution of your evolution. So here n is the cube root of the total number of co-location points in the initial data scheme. And then the delta x's are the differences in evolution resolution. And you see here the N47 being the highest resolution, initial data resolution. The red and the green curves, so the top two curves are just the difference in evolution resolution, and the bottom two curves are a difference in purely initial data resolution at the highest evolution resolution. And so we see a very clear convergence with regards to both resolutions. And we see that the evolution resolution is the dominating factor in our evolutions. So this gives us some confidence in our initial data codes and the results that we're providing.
And can I interrupt you for a second? Probably goes back to the slides. Alex, do you want to speak up?
Sorry, am I missing chat messages?
Sure. Can you hear me?
Yeah.
Thanks. So I was wondering, when you say maximal slicing, but you're still using the assumption of conformal flatness when you solve the initial data, is that correct?
Yeah.
Okay, so that means that you achieve the maximum value of the spins that you can have within that approximation. Within that with the limitation given by conformal
Absolutely.
flatness.
Yeah.
Okay.
So
Thanks.
yeah. So in case of black holes, you're stuck at what, the 0.8 or 0.85, and in the case of neutron stars, you hit mass shedding before you have any issues, really. So.
Okay. Okay. Thank you very much.
Sure. Okay. Further questions?
So I don't see anything else in the chat, so you can continue. And don't worry, I monitor the chat. I forgot to say in the beginning.
Okay. Yeah. Thank you. I appreciate it. Next, we showed a comparison of eccentricity reduction. So this is an asymmetric BNS binary with very different spins. So the smaller has an irrotational spin, and the larger has a spin of 0.6. And here you see that quasi-equilibrium, it's a necessary starting point for us because we start the initial data from scratch, essentially, with regards to the shift. And so we need the assumption of, in this case, the force balance equations in order to get a good estimate of our binary. But this gives you a very eccentric in spiral. Just using 3.5 PN, we can already significantly reduce this or improve this, which is this blue line in the middle. And then for those interested, you can do iterative reduction procedures in order to essentially flatten this out. So in our codes, we have a way to automatically do the 3.5 PN estimates when the user wants them, because it's even in this case. So you see that this is a highly spinning primary. We're still just using the 3.5 PN estimate that doesn't include the spin orbital coupling or anything like that. This is just the basic 3.5 PN estimate, and it's already significantly superior to the quasi-equilibrium estimate.
I think we have another question in the chat.
Please.
What's the maximum mass ratio supported for a black hole neutron star system?
The maximum mass ratio is that I haven't taken it to a maximum mass ratio. So right now, the black hole neutron stars are done in such a way that I've taken it down to a Q of 0.2, and that was reasonably easy to do. Going below that, so even smaller mass ratios, depending on how you look at it, I have to fix some things on the neutron star, because the resolution around the neutron star gets too stretched out. And so that's something that I have on my list to do right now. So right now, I would say Q of 0.2 is reliable, and going any further down requires much higher resolution. I would say inefficiently, because you'd have to increase the resolution of the total computational space. And yeah, I intend to add spheres around the neutron stars to reduce that. So yeah, that's my answer for right now. But really, like testing the extremes of the initial data, there's too much to do, and I haven't taken it to the extremes in a lot of these cases.
Okay, thank you.
Yeah. Okay, I'm sorry the video is choppy. Maybe it's a little better now. But yeah, this is a black hole neutron star binary. You can see it's a little bit about 0.23 cube 0.23 with fairly high spins on both. So well, I guess for the black hole it's about mid-range, and for the neutron star it's on fairly high spin. And below that are the evolution parameters. So this is evolved with a Z4C. And so that's the eta and kappa term and the resolution. So on the left, you see an evolution of the log density. And on the right side, you see the orbital track. And the thing to keep in mind is that this was imported directly, like nothing special was done, like hand tuning to the initial data or anything like that. And you see a very smooth in spiral. Okay, you can look at the plot and see that it should be smooth, even if the video is choppy. And you don't see any drifts. You don't see any crossing of the lines due to eccentricity or anything like that. This was an eccentricity reduced data set. So this was like after 4 iterations as just like a proof of concept of what we're capable of doing. Yeah, so on the demonstration side, the solver layout or solvers layout, all of the codes include a setup, a solve, an increased resolution, and a reader. So the setup sets up the numerical space and initializes your fields. The solve obviously solves the system. The increased resolution, you can run an initial data set at lower resolution and then actually reuse that initial data to increase the resolution and run it at a higher resolution. Or you can, if you need a more optimal domain decomposition, you can run it at the same resolution. And yeah, there's some nuances to that, but yeah, for now, just stick with increased resolution. And then there's a reader. This extracts all the diagnostics from the actual solution. So you can actually get an idea of how consistent the solution is to what you were expecting and give you some other just useful feedback. Reusing initial data for us is essential. CADEF is very computationally expensive. The solver just does a huge Newton step, so it solves the entire system of equations. This is how we can get such a consistent solution, because everything is solved together. But at the same time, it's very demanding, especially on the memory side of things. So here I've included some benchmarks for a system using 128 cores. And this is for what we consider to be low resolution. Yeah, just to give you an idea. So this is not a laptop initial data system. And if you go to high resolutions, it's not something to be run even on a single node in the case of binaries. But in order to mitigate that, again, we have not run into, aside from highly asymmetric like binary black hole systems or black hole neutron star systems, essentially everything can be done at low resolution, especially in the case of binary neutron stars. And then you can always, if you feel the need, run at higher resolution later, which is a huge advantage.
Sorry, can I?
Yeah.
So just to go back, so you are, to make sure that I'm understanding, so you're saying you're solving all the equations, including all the equilibrium condition at the center that aren't elliptic equations at the same time, not the seesaw thing that most other codes are doing, where you solve one equation,
right? So
and then the other one, and so on and so forth.
Right. So there's a little bit in the case of the binary neutron star. So the BNS is probably the most. We never do the seesaw approach. We only move forward. So I'll answer that directly. We always move forward, but there are some steps that have to be taken, especially with regards to asymmetric binaries and eccentricity reduction. in order to do the so in the first stage of the BNS, you solve the whole system consistently, but you're left with some leftover ADM momentum, usually in the X direction, I believe. And so in the next stage, we rescale the matter. So at this point, you fix the orbital velocity, and then you rescale the matter based off of your baryonic mass that you're expecting for both stars. And this is possible because, I mean, your baryonic mass is just a function of your Lorentz factor. And so so you get a very, I think it's on the order of like 10 to the minus 3, 10 to the minus 4 of a rescaling of the matter terms in order to fully reduce the linear momentums. So there are stages that take place, but there is no going forward and going backwards. Like it's not, yeah, you solve for, omega, and then you fix omega, and then you solve something else. We solve, in the first stage, we solve omega based on the force balance equations. And then in the second stage, omega is fixed in order to rescale the matter to reduce this linear momentum. And then the same recipe is applied to eccentricity reduction, because eccentricity reduction is just fixing the angular frequency and introducing this expansion factor. Yeah, does that answer your question, Nolan?
Yeah, it does. Thank you. I just wanted to make sure, because I think I know of one other code that does that, so you're kind of unusual in that respect. Thanks.
Yeah. I mean, I think a lot of codes see it as an efficiency thing. We try to increase the efficiency by having, what's known as the better guess in spectral methods, which is why we reuse the initial data from neutron stars in order to set up our computational domain for the BNS, which I'll show. So there's some things that we tried to reduce this, but at the end of the day, you do end up with a huge Jacobian that has to be solved. So the memory requirements scale quadratically to that. Okay, so on the demonstration side, I'll try to quickly go through this. When you first get into the initial data directories, all of them start out without any sort of default setups. Because the BNS, as I mentioned a second ago, utilizes the isolated TOVs as its initial guess, we have to start with the TOV. So in the case of starting with the TOV, let's see if I can turn annotations on. Yeah. Okay. So we run the setup, and it generates these init NS and DAT and info files. So the DAT is actually what's storing our numerical space and our scalar fields, our variable fields, and the info file. You can think of it as like a par file, but it's really a lot more than that, because all of our initial data can be reran through the solvers, and you get a solution back. Well, it should immediately tell you that it's a solution. It's also tracking these quantities that we need in a fashion that we can modify and reuse. So this is an example of what the info file looks like. The initial section can be disregarded with regards to the solving. This was implemented as a way to keep track of how we got to the initial data that we have now. There was a time where things were a bit more uncertain, and this was necessary. Today, this is much more stable, and it's more just kind of a nice to have. The real section is this neutron star section, which describes the numerical grid setup. So you have these radii, which have been used to construct the numerical grid, and also scalar quantities that are used in the actual solver themselves. So things like MADM or baryonic mass or quasi-local MADM, these things are actually used in the solver and are updated every time, every iteration. So if we wanted to modify this to be something else. So you decide you want to do a different configuration. The only thing that you have to worry about is the chi fixing parameter and the ADM fixing parameter. There's also the option to do baryonic mass fixing. You can look this up in the README, but for today we're just doing the ADM mass, since especially in things like LIGO and all the astrophysical observations, everyone's talking about the total mass of the system, which is always the ADM mass of the constituent in isolation. So that's why we solve everything by default with the ADM mass. Here there's also describes the equation of state that's being used. In this case, this is just the cold slice, beta equilibrium of Togashi, and a cold table. We can run this through the solve routine. As I mentioned, it's just called solve. And the top is just kind of an example of the type of output that you would see during the solving routine. Tells you kind of iteration, where we're at error-wise, how certain physical quantities are changing throughout the iterations. And then at the end of an iteration, you see what the final, the new error assessment is. Next to that, this EQ first int is actually saying which equation is kind of holding up the solving routine. So what has the highest error associated with it, and which domain that it's in. And then you have some timing statistics after that, and how the system of equations are broken up amongst the nodes, or the ranks in this case. So I've saved this all to Togashi. You can a Togashi folder. You can see this converged, this converged name. So it's all in the same format. It's always converged NS. And then you have mass, spin, resolution, and then .dat and .info. It's important to know that there is no equation of state written in the output name. So if you do two different equations of state with the exact same parameters, they could get overwritten. So it's important to put it into folders, and that can be put into the solve command. So yeah, it gets outputted into the directory of choice. But now that we have this solution, maybe we want to do something else with it. Maybe we want something higher mass, higher spinning, or whatsoever. So we can, you can just copy it so it doesn't get overwritten, and we can look at the info file again, and we can just say, okay, I want the same system, but I want a different chi and a different NADM. And on the right side, you see again, now we're just solving the same thing. Only in this case, it's rotating. So our degrees of freedom are higher. If you're paying attention, this was the degrees of freedom nearly doubled. And this is because you now have to deal with the shift component since we have rotation. And then it just solves the system using our initial solution as the initial guess, which is going to be a bit faster. Not in the case of a single neutron star, not huge, but it's helpful, and you don't have to start from scratch. So that's always nice. And now if you want to change the equation of state. So if you ran the setup initially and you're like, I don't want Togashi, I want something else. We can change the EOS file and EOS type. So by default, the EOS directory that it looks in is this cadet EOS directory, which there's some basic polytropes and cold tables that we've included there. But you can also just specify the directory where it says EOS file. So I could just put, current directory / whatever the name is of my polytrope, and it will then just search the current directory. You're not tied to this EOS directory at all. In the case of a polytrope, so I've chosen a polytrope here. The EOS type has to be changed to cold piecewise poly.
Quick interruption. We have about half a minute left. I'm sorry, I think the timer didn't alert you today.
Yeah, it wasn't. Okay, all right.
I'm so sorry. Yeah.
That's okay. Thank you.
If you can finish the example, that'd be great.
Okay, yeah. So we changed these two, and we actually feed this back into the setup routine, and this generates an ideal setup for this equation of state. Okay. this generates an initial setup based on this equation of state and the ADM mass that was supplied, and then you can just rerun the solve routine from there. Yeah. This is just an example of using an increased resolution, where you run the increased resolution and your converged solution with a base file name and a resolution, and you can then just rerun this this base file name and get your higher resolution solution. And it's in fewer iterations than it would have taken before.
Okay, so I'm sorry to interrupt you again.
Yeah.
Because
Okay.
I think we are really in the break time already. So if you could just conclude, that would be amazing, and then maybe take a couple of questions.
All right. All right. I'll just leave it at my summary slide. So yeah, I went over everything that we have and tried to get through the demonstration. But yeah, if there's any questions, please.
Okay, thank you so much, then. That was an amazing time.
Sure.
Yeah, and sorry for interrupting you, but yeah, I think the timer was off.
No.
Do we have any questions
Okay, yeah.
from the audience?